Hi guys, Buildzoid here, and today we're going to be taking a look at another RTX 2080 PCB. This time the ASUS Strix. As with the other cards that I've done on my own channel, this photo comes from Tech Power Up, so you know, big thanks to them for providing high-resolution PCB pictures on their website. And with that out of the way, let's get right into taking a look at how this is actually like set up and if I like it or not. I actually do like this PCB a lot. It's not that different from all the other 2080s that are out there, the ones that go a little bit custom, because basically all of the 28 RTX custom RTX 2080 PCBs can be basically summarized as 10 plus 2 phase using some form of 70 amp power stage. That's pretty much all of them right there. Every single one of them looks like that. At least I think that's what we're going to end up looking at. Because so far, there's not been a single card that has deviated from that. So, yeah, I don't expect any differences. But ASUS seems to have gone a few steps further than everybody else. I mean, they still have a 10 plus 2 phase, but it's just more interestingly implemented 10 plus 2 phase with some minor tweaks here and there to it. So anyway, let's get right into the minor rails, get those out of the way, and then move on to the interesting stuff. So we have a bunch of single-phase, fully integrated voltage regulators along here, and I don't know which one's what, but they're going to be 1.8 volts, and this powers your VPP rail for the GDDR6, as well as the BIOS chips that NVIDIA uses. They use a 1.8 volts BIOS. There's going to be a 5 volts rail, because guess what these run on? They don't run on 3.3 or 12, they run on 5, so we need a 5 volts rail for that. Then we need a PEX rail for the PCIe interface of the GPU core, and then we need a USB-C rail, because you can't actually just run a you can't run a USB port off of the straight 5 volts. Also, because if for some reason you shorted the USB-C port, if that took down the 5 volt rail, yeah, your card would not be happy with that happening. I mean, it would just shut down the VRM, but that would then, like, you'd have to restart the system. So, you know, you want to keep the USB port on a separate voltage regulator so it doesn't take down the whole system when something shorts the USB port. Anyway, so that covers the minor rails. They exist. I don't know which one's which, but they're here, and yeah. I'd guess that, like, this is 1.8 volts. That's... I'm not... Well, I have no idea. They're, like... Because these two seem to be the same regulator, and these two seem to be the exact same regulator as well, and I'm not sure, like, what the current draw differences are between these. 5 volts should be one of the smaller ones, so... As well as 1.8 volts should be one of the small ones. And then PEX and USB-C would probably be this and this. And I'd be inclined to think that this is PEX and that would be USB-C. Though, it could go either way, honestly. Actually, well, this seems to have a power plane stretching towards the GPU core. Yeah, I have no idea. Or this could be USB-C. So, it doesn't matter. If you have the card and you want to figure out which one's which, I mean, you can just measure the voltage coming off of them. One of them is going to be sitting at 5 volts, one at 1.8 volts, and one of them is going to be sitting at 1 volt, which is the PEX rail right there. So, that's going to be 1 volt. Or something around 1 volt. It might be like 0.95. Let's not make that a negative sign. And the USB-C rail, I actually don't know. Well, you could just check what's connected to the USB port for that one. Anyway, let's get on to the interesting VRMs. The lovely 10 plus 2 phase VMEM and vCore VRM located over here. And that down there is vCore. And this, like, let's just consider why this, like, let's just talk a little bit about why they might have moved the GPU core this high up. Because, quite frankly, when I first saw this, I was just like, the hell are they doing? Like, there's no logical reason that you'd want to move the GPU core up by whatever this distance is. Like, I get why they have the taller PCB, okay? There's not much you can do about having 12 phases and needing to put them somewhere. There's not a lot of space down here. You have a power plane over here. You can't really put the memory on top of the... Like, unless you want to have a million PCB layers, you really don't want to put that on top of the vCore power plane, which we have right here. But that doesn't explain why they had to move the core up so far. Like, the core could have just... Like, the core could have lived down here, right? just as happily as it can live up here. Like, they could have basically moved an entire core down, and then maybe, like, moved this one, like, moved these, you know, moved all of these guys, like, sort of circular fashion upwards. And then the power plane for the memory would just have to, you know, extend a bit further downwards. But I've actually, so, you know, it's kind of, but I've actually thought about that a bit, and I think they're doing it to get the core kind of closer to the V-Core VRM. And it doesn't, like, this distance obviously doesn't change, but if you actually look at how the power plane is routed, you can see that, like, that seems to be roughly how the power plane goes. And if they move that core down, that would actually have to go, you know, down along with it. Like, you'd have more distance to cover. So I assume that's what's going on there, because I can't think of any other reason why you'd want to move the core that far from the PCIe slot. But basically what they've done is that they've kind of centered the core against the V-Core VRM, which basically means that you have less distance from, like, the top phases up here as well as the bottom phases to the GPU core itself, which should, in theory, have some benefits for power delivery to the GPU core, because less distance means less power plane resistance, means less voltage drop, and easier time regulating the voltage delivered to the GPU core. So that kind of makes sense, but I'm not sure how much of a difference that actually makes. I'd think it'd be pretty marginal, but, you know, I guess they were like, well, we're going to be making a massive PCB anyway, and it's not like we need to, like, they make their own coolers, so it's not like they need to accommodate some specific heatsink design, so they're kind of free to move the core if they feel like it, even for, like, marginal benefits. But it is an interesting thing that they've done, is just like, yeah, the core's in the way up there. The other thing that ASUS have done with this V-Core VRM, which is kind of special, well, it's not super special, but what I've noticed about a lot of the other RTX cards that we're seeing, like the custom ones, they don't really go, like, they either use the same output filtering setup as a reference card. You know, take a look at the 2080 Ti Gaming X Trio that we had here. You know, like, MSI loaded that thing with extra capacitor mounting points and then just didn't use any of them, and just stuck to whatever the reference design had. And then some of the other cards basically look exactly like some of the other cards I've seen so far do the exact same thing, where it's just like they use this, like, reference output filtering as far as the capacitors go. And ASUS actually hasn't done that. So on this side of the card, you obviously have all of these lovely capacitors over here. And these are just your standard, well, yeah, standard for ASUS, aluminum polymers from APAC. So that's a Taiwanese capacitor manufacturer. They're really common. And I've not heard of these having, like, the thing is, ASUS uses these on, like, all of their motherboards. And Gigabyte uses, like, all of the motherboards below $150. ASUS uses these everywhere. Gigabyte uses these everywhere. And I've not really heard anything about, like, ASUS motherboards or Gigabyte motherboards having mass capacitor failures, so it's just like, these are fine. There doesn't seem like, I don't see any issue with them being, like, not a Japanese capacitor. They're still rated for 5,000 hours at 105 degrees, which is pretty standard for your aluminum polymers, which, well, actually, it's a little bit over, like, it's a slightly higher rating than 105 degrees Celsius, and I can't fit that. Let's just put, oh no, I can. Which is pretty standard for, like, aluminum polymer capacitors. That's, like, your normal rating, though if you're going for, like, bottom of the barrel aluminum polymers, you'll get them at, like, 2,000 hours instead. So it's a decent upgrade. And at the top end, you'll be looking at, like, 10,000. Or if you're ASRock, you're going to go all the way to, like, 12,000. So, you know, this is basically standard for a GPU. There are more expensive, like, there are better capacitor manufacturers out there, but it's just like, I don't see anything wrong with these. But the interesting thing is ASUS has put on all of these, right? And they've still kept all of the output filtering capacitors that you'd see on, like, a reference card. Like, that is still the same output filtering as the reference card. And these are SMD aluminum polymers. These are awesome. And then they've just loaded the board with extra bypass capacitors just going towards the core. And I actually think the core bypass capacitors, like everything you have right here, is actually the same as reference. But yeah, they've added a whole bunch of extra output filtering. So that's kind of neat that they've done that. I guess along with the funky power plane, they're hoping that their cards clock like 10 megahertz better on average, which is roughly how much difference I would expect from all of the things they've done, if even that. Maybe on liquid nitrogen it would make a bigger difference, but on ambient cooling, yeah, I don't think that actually makes much of a difference whatsoever. But it's cool that they've done it, because a lot of the other brands, as I said, they'll just kind of, you know, they'll add 2 phases and keep the reference design, which is just like, okay, well, I mean, you did add 2 phases, so you did something, but at that point it's like, you might as well have just kept the reference PCB. And they've done the same thing for the memory VRM, where actually the ASUS memory VRM has way more output filtering capacitance than what you would normally find on these cards, which is kind of neat, because in the past with some of the 10 series cards, I'm not saying a lot of them, but just like well, I've not tested a bunch of them, but like the 2 10 series cards that I worked with, both of them seemed to benefit when well, no, didn't seem to. They definitely benefited from some extra capacitance on the memory, on basically the memory voltage rail, which was kind of interesting that was a thing. But yeah, so ASUS is just kind of going to town with the extra capacitors on this thing, which is kind of neat. Obviously, it adds manufacturing costs, and as I said, for, say, the core clock, I think the benefits are marginal. For the memory clock, they might be kind of significant. You know, really depends. Somebody would have to test, like, a bunch of cards to see if there's really any major difference there. But yeah, so that's kind of interesting that they've done that. Now let's move on to the actual power stages and controllers. So ASUS for this card is using, this is the chip that controls the vCore VRM, and that is the ASUS favorite MP2888. Yay! And that's a 10-phase voltage controller. And at this point, I've finally confirmed that the UP95, like the UP9512 is definitely just an 8-phase, and the MP2888 is a 10-phase, which is really interesting because like NVIDIA does interchange, like the Founders Edition PCBs can technically fit both of these, which is kind of weird that they've done that. So yeah, I'm not entirely sure how that is like working out, but the thing is like with at least with the UP9512, it's really obvious that you have only like what is it, 8 current balancing circuits hanging off of them, which you can't see on this, because like I assume the current balance is this set of resistors right here-ish. But the problem is, like, it's really hard to check that, because I don't have the card in hand. If I had the card in hand, it'd be just a matter of measuring the resistances between the power stages and how they're wired up. Like, either the PWM signals or their current sense outputs. Because if the current sense outputs are going in, like, into the same circuit together and then into some resistors and then end up going to the same pin, then it's like, okay, those aren't running separate. Those are just being added up. And the controller sees them as 1 phase, not 2. So yeah, but without the card in hand, it's just like, well, this looks like it could have 10 current sense inputs, whereas the UP9512 cards all definitely have 8. Like, it's really visible that they just have 8, not more than that. So yeah, that's the control situation. So this is a real 10-phase, which is kind of neat. And at least it should be a real 10-phase. I'd love to confirm it, but I'm not paying NVIDIA for a 20 series card, and I'm not going to get sampled either. So yeah, but this is almost certainly a real 10-phase, and this is where we get to the other cool thing that ASUS has done. They're actually not using the typical Fairchild Semiconductor FDMF3170. They're using a CSD 95480. And the reason why this is, and I just wrote over a chip that we're going to have to move that a bit. Okay, so I'll just write it here. No, that doesn't fit. Down here. So that's a CSD 95480. And that's a 70 amp power stage, as usual, but it's made by Texas Instruments. And unlike the and compared to the FDMF3170, this thing is ever so slightly more efficient, which basically means that this card has an ever so slightly more efficient 10-phase than all of the other 2080s out there, because everything else I've seen so far runs a 3170, and the reference card is an 8-phase. So this VRM is slightly more efficient. like 3 watts more efficient, which is just like, I don't know if anybody cares. But it's worth well, depends on how much load you're putting into how much you're loading the card up, but it really is like the biggest difference at like 500 amps output. You're going to look at like 10 watts less heat output on this VRM compared to the one using FDM F3170s, which is just like, well, it's a difference, all right, but good luck like noticing it, you know. So anyway, let's talk efficiency figures for the full range. So as usual, because these are 70 amp power stages, they're spec'd at 1.8 volts output. I don't know why. Also, well, the data sheet's also spec'd at 5 volts VCC, so that's the 5 volt rail that I mentioned earlier. And they run at 600 kilohertz, which the FDM F3170s are entirely spec'd at 500 kilohertz, though their efficiency doesn't change too much across the switching frequency range. At least until you get the really high currents. At high currents, it's just like 500 kilohertz is best. These are spec'd entirely at 600 kilohertz, 5 volts, and so 1.8 volts out. Wait, will I have enough space? Let's put that there. 1.8, 1.2, there. So, and as usual, going from 1.8 to 1.2, I'm just dividing by 1.25 because that's the same, that's what I like. I stole that scaling off of a IR3575 data sheet, and that's what I've been using for all of the other power stages as well. Well, the 3170. And so basically this is just to keep consistency, and it should give us a better idea of the actual real VRM efficiency, because at one point, like 1.8 volts is way above what this VRM is going to be actually outputting. So yeah, that's why I'm scaling it down to 1.2 volts, even while like using a different data sheet. It's just like, that's going to be closer to reality than whatever this 1.8 volts figure is, because it's going to be way too high just because of the high output voltage. So let's get into the current figures. 200 amps, and I didn't manage to fit it. Good job, me. So 200 amps, you're going to be looking at about 17 watts of heat output on this VRM at 1.8 volts, whereas the reference card would be about 20. So there, that's why I said there's like, well, no, the other 10 phase 2080s, you're going to be looking at about 20. So yeah, there's like no difference. And then at 1.2 volts, you'd be looking at more like 14 watts, whereas the other cards would be more like 16. So, you know, very small improvement there. And 200 amps is probably pretty close to the stock current draw of a 2080 before any overclocking. Now, with overclocking, you probably, well, the power limit will probably stop you before you get anywhere near that, but if you somehow did get near that, you still wouldn't have anything to worry about, as at 300 amps output, this VRM would produce about 30 watts of heat, which, well, I mean, if you didn't have a heatsink on the VRM, you'd have a problem, but it has a heatsink, like a good one, built directly into the heatsink. Like, the cooling system of the card is pretty substantial, so I wouldn't worry about that. And if you were doing like extreme overclocking with the card on a like with a core only water block, or, you know, an LN2 pot, if you just throw a fan over the VRM, it won't get hot enough to not finish a benchmark, right? Like, that's the main concern, is just like will it overheat before you finish the benchmark? And it's worth noting that, which I forgot to mention, is these aren't just regular power stages. These are actually smart power stages, so SPS, smart power stage components. And the thing that's special about these is these integrate current monitoring and over current protection, and they also integrate temperature monitoring and over temperature protection. So this VRM will actually shut, like, the power stages themselves are capable of shutting down the VRM if they get too hot, which is kind of neat, because basically it means you don't need to worry about like overheating the VRM, because it'll shut down before anything goes super bad. So yeah, that's pretty cool. Anyway, 300 amps, 30 watts at 1.8 volts, you'd be looking at more at like 24 watts at 1.2 volts. 400 amps output, you're going to be looking at about 48 watts, whereas at 1.2 volts, you'd be looking at about 38 watts. And this is all slightly less than like the other 2080s out there so far. I don't know if there's going to be any other 2080s using the CSD 95480s. There's also the 95490, which is a 75 amp part, if, you know, anybody wants to try go a step above what ASUS is doing. You could also try more phases. That also works. But 500 amps output, you'd be looking at about 75 watts of heat. And this, like, 500 amps is, like, well into the LN2 overclocking range. And I would assume you'd need, like, around 1.5 volts for that at that point. And that is if the card even scales to that much voltage. Who knows? So far, nobody's put one of these on LN2 seriously. I'm so sad about the state of 3D benchmarking right now. Like, I remember when the 780 Ti launched, it was like for a week or two, like for basically a month, EVGA and ASUS were trading the first place in 3D Mark. And the 2080 launches, and nothing. Like, nobody is doing anything on LN2. Like, Kingpin posted like single card scores, and other than that, there's just been nothing as far as the 2080 Ti goes. And it's just so sad compared to what happened when, like, the 780 Ti dropped, and you just had, you know, like, you'd go check who's first one day, and it'd be ASUS, and then you'd check the next day, and it'd be EVGA, and then you'd check the next day, and it was ASUS again. And it was just like, that was great, that was awesome. And now it's just like, oh, well, it's Kingpin at the top of single card, and dual card is held by Gamers Nexus or JZ2 cents on water. And it's just like, well, that's boring. Yeah, and the 2080s aren't really getting much more attention either. Anyway, so LN2, 400 amps would, dry ice would probably even touch into the 300 amp range. Because these things, the thing about the, like, at least for the 10 series, it was really about the temperature. Unless you get the card really, really cold, they really wouldn't run very high voltage. So, yeah, on dry ice, you probably wouldn't get into the ridiculous current ranges that LN2 can do, just because on dry ice temperatures, the voltage wouldn't scale as far. It's not like 1.5 volts on dry ice would clock very well. So, yeah. And then the rest of it is just like, this range is very much ambient. But the VRM is nice enough, slightly more efficient than all the other 2080s out there. And 75 watts, like, that's definitely coolable for benchmark purposes. If you just, you know, put a high RPM fan over it, that's fine. I'd be completely confident taking this on LN2. The only complaint I have is that they did move the core up so far. Like, this is going to require a lot of padding to keep the LN2 pot from, like, leaning the card way over. Because the LN2 pots are ridiculously heavy. So when you have it sitting in a test bench, they tend to, like, tip the card over, and it's just, you need to pad it a lot. And this would just mean more padding, which is kind of annoying, but not a huge, like, it's not a big deal. It's just like, well, that's very inconvenient. Instead of, like, 4 blue shop towels, I need, like, 6 or something, or 8. Actually, more like 8, but yeah, you get the idea. So, you know, lovely, more efficient 10-phase than everything else out there. ASUS just can't stop themselves from minor upgrades in every way possible. And the memory VRM is a similar story where you're looking at slightly, very, very, very slightly higher efficiency, because keep in mind, VMEM doesn't need to push much current in the first place. So upgrading, like, you know, upgrading this makes even less of a difference than the upgrades they made to the vCore VRM. So, you know, instead of 20 amps producing 2 watts of heat, you're looking at around 1.5 watts of heat. 30 amps, instead of producing about 3, you're going to be looking at about 2.5. And 40 amps, instead of producing about 3.5, you're going to be looking at about 3. Actually, wait, no. Instead of producing about 4, you're going to be looking at about 3.5. So, yeah, basically half a watt, slightly more efficient memory VRM. Which is just like, okay, well, that's a huge amount. Like, it's still an upgrade. It's just like, that's basically irrelevant. But at this point, like, the thing is, at this point, they're already using these CSDs all over the vCore VRM, so it just makes sense to use them again for the memory VRM. And that's a 2-phase using a UP9512Q, which is a low phase count variant of the UP9512. UPI Semiconductor still hasn't put up documentation for the UP9512. I'm really annoyed about that, because I'd love to see the data sheet for this thing, and it's just like, no data sheet. And yeah, sucks. So that kind of sucks. But yeah, that is still a true, you know, that's definitely a real 2-phase. That chip's definitely capable of that. And it's slightly more efficient. So other neat features on this card, you get a BIOS switch. ASUS is basically using it for a quiet mode and a performance mode on the card, which you know, one is slightly faster, one spins the fans less. What's also neat about this card is that ASUS is still doing voltage mod points. The only problem is NVIDIA happened, and so they won't label the damn things. It used to be like ASUS puts these on like all of their cards, and normally on like some of the older cards, they'd be like V-Core. Oh right, that's the end of the layer. So V-Core, VMEM, and then VPEX. Right, and you just have them labeled like that, and if you shorted the pads next to it, that would enable voltage mods, and you could then volt mod over these really convenient, you know, solder points, instead of like messing around with SMDs on the PCB of the card, which is a bloody pain. But then NVIDIA happened and told ASUS, look, if you label these things, we're going to stop giving you chips. So now they don't label them, which is really annoying. But it's neat that they're still there, and hopefully someone from ASUS will release information on how these are actually wired and how to enable them. Because, like, well, I don't think anybody actually really wants to put a 2080 on LN2, but if somebody out there does, then, you know, they should be able to. I mean, they paid for the bloody card. So, yeah. But ASUS just puts these on all their cards. It's just unfortunate that recently they haven't been allowed to label them anymore. Yeah, NVIDIA really doesn't want you to have voltage control over their cards. Anyway, moving on, we also have a bunch of current balancing stuff. Of course we do. It's a 20 series card. These wouldn't be finished if they didn't have current balancing. So, I'm actually not sure which chips are what for that. So, well, no, I know some of them, but not all of them. So I'll just go on the back of the PCB and list them off. So as usual, for current monitoring, you're looking at an NCP 45491. And there's two of them, and they're going to be these two chips. Oh, so I was right. It is those two. Anyway, so you have the NCP 45491s. Those can each monitor 4 shunt resistors. Yeah, the data sheets for these are public, which is pretty neat. And then for the actual current balancing itself, because these just report how much power is going into the GPU, the actual power control, like the power balancing is actually done by a UP7651Q. And there's no data sheet for those. So that kind of sucks. And those are like 2-channel current monitors. And you can actually kind of see what's going on with the current balancing because you have all of these like split power planes. And like there's a phase down here, there's a phase there, there's a phase there. And you can see that these two phases share a 12-volt source. This one has its own little 12-volt source. These 3 are on one 12-volt source, you know. So then these 2 are on another 12-volt source. These 2 are on a 12-volt source. This one is on, I think, a separate 12-volt, and these are obviously the memory phases, and those are each on a different 12-volt source. And the reason why they do this and split up the VRM like this, which is just extra work for board design, you know, if you were sensible, you would just go, screw it, we're just not going to check how much power we're pulling through the connectors, we're just going to worry about how much total power the card is pulling. But basically, they split up the power planes like this so that they can basically go like, okay, you 3 phases, you can now use the 8-pin. And then when these start pulling too much, they can just drop those off and say, okay, you 3 get the 8-pin. Or, well, more like, you 3 can now pull from that 8-pin. Though really, it would be more like these, like you'd have like 5 phases like this, let's say. And they'd be all sitting on the 8-pin. And then you start pulling too much current, so the 2 phases down here would go from being on the same 8-pin to the other 8-pin, and that would then rebalance the current, the power distribution. But if you actually did that, you'd also probably want to trade like this single phase over from this 8-pin to the other 8-pin, which is why they have so many different power, why you have, you know, so much current balancing circuitry. Because if you actually look at the card, right, you have all of these random MOSFETs sitting around, as well as like these guys, which are the big current balancing circuits. But like these, I'm also pretty sure are just more current balancing. And then if we go on the back of the card, we have these, which are, I assume, yet more current balancing. So yeah, it's literally just for switching the 12-volt power sources into the phases. so that you don't pull too much power through one specific power, one of the three, because these are all individual 12-volt sources, right? And then you have the PCIe slot. So the thing is, NVIDIA has a per power connector power limit. So even if you had even if the whole card is technically below its TDP, you could still be bouncing off the power limit of one of your 8 pins instead of, evenly distributing the power consumption between all of your available connectors. So it kind of reduces the amount of power throttling the card would do compared to normal. The other option is that you just don't worry about how much power you pull through each of those power connectors and just worry about the total power limit. So, yeah, but NVIDIA likes... I don't know why they actually care so much about this. It's just like, if you look at, AMD cards, it's just like, if you slightly tweaked a Vega card's power planes, it wouldn't know if there was one 8-pin or two. Or, well, actually, no, it's more like... A Vega really doesn't care how much power it's pulling from which 8-pin. It just cares that there's not more than X amount of power coming out of the VRM. So, a Vega basically doesn't have any current balancing whatsoever. And this has more current balancing than I think is absolutely than what was ever necessary, just because NVIDIA feels like it. So, yeah, that's kind of that. If you want to lift the power limits, then you can apply lower resistance shunt resistors on top of the existing ones. I would recommend something like 0.003 milliohms onto this one as well as this one. And that way you should get about a roughly 2.7 times increase in power limit, because the reported power consumption will be about 2.7 times lower than what it would normally be for these two power connectors. So that's what's going on with the current balancing, which I think is completely unnecessary. It's fixing a problem that NVIDIA created when they started worrying about how much power they're pulling through each power connector, right? Because, again, if you just didn't worry about which power connector your 500 watts is coming from, there wouldn't be a problem. You wouldn't power throttle. So, yeah. Anyway, that's it for the RTX 2080 Strix PCB from ASUS. I like it. I really do like what ASUS have done here. It seems like it also, I think also the Strix cards are, ridiculously expensive again. So, I mean, I can see why they're expensive, but I'm going to also say that for most users, the difference is going to be extremely marginal. They're slightly more efficient. They might clock on average ever so slightly higher. As I said, 10 megahertz core clock, maybe. There might be a bigger difference on the memory. I'm not sure about that. But, yeah, it's a nice enough PCB. It's just if it's really expensive, I wouldn't say that you should, if you're comparing cards and, the Strix doesn't have, well, even if it had a slight cooling advantage, I really wouldn't go for it, because it's the main thing is just, cost, in my opinion, right? If the difference between, this and the Gaming X Trio card was $100, I would just tell you to get the MSI card, because it's... the extra $100 really isn't going to make much of a difference at the end of the day. Sure, you're going to get a nicer PCB, but you're not going to see the benefits of it in daily usage. But I do like the PCB. It's just it really depends on it if the pricing for it is acceptable. So, yeah, that's it for this video. This one's really, really long because, yeah, it's really, really long. Yeah, so thanks for watching. Like, share, subscribe, leave comments, questions, suggestions down in the comments section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon, PayPal, and t-shirts. There's actually new t-shirts coming out. I'm redoing the whole Teespring store, so there's already new shirts listed. They're just I need to finish stuff up with the shirts, but there's one new shirt design basically coming out in all of the different in a whole bunch of different sizes available. Unfortunately, it's only going to be in white. So yeah, that's it for the video. Thanks for watching, and goodbye.